There are many spaces which contain mathematical objects, such as vector spaces, which contain vectors, metric spaces, which might try to define the distances between objects, sort of like a ruler would. Groups would be something like integers. All the integers are a group. Manifolds are interesting because, sort of like a sphere, at any point on the sphere, it always looks the same, so that's a manifold. And a field would be something that we might be able to represent sort of like that. Well, all these spaces have some laws that they have to follow, so we're going to try to define the laws of the vector spaces. So all the spaces we're going to look at today are just going to be vector spaces. Let's start by defining real space. We're pretty familiar with this one. It's usually called all real numbers. So we could define it as R. And we realize that R is only one dimension, so we're just going to call it X with a little bracket there. But we have to define where we got X from. So we pulled X, we could say X is an element of, we pulled it from negative infinity to positive infinity. These parentheses here are just saying that the infinity is actually not included here because, well, infinity is not a real number. Well, it looks really complicated on paper, but all we really did was just define all real numbers as being this number line that goes from negative infinity to infinity. That's all we've done here. We've decided that along this number line, you can call any one of those points X, and well, X is going to be from negative infinity to infinity. Well, that was fun, but now let's do it in R to the third. So now we have 3 dimensions. This was just 1 dimension, so we just had X. But now we have to use X, Y, and Z. We'll put a little bracket around this. So now we have a 3-dimensional vector. But we had to say that X, Y, and Z came from somewhere. So they were all an element of this R. So we already defined R, so let's just use the R now. This symbol right here just simply means element of. So X, Y, and Z are an element of the real numbers over here. So you basically pulled an X, a Y, and a Z from over there. Remember that this is R to the third. So even though we pulled 3 values from R, it's basically going to be R times R times R. So these 3 values are essentially multiplied by each other. So if you had R2, you'd get a 2-dimensional space. But if you had R3, you're going to get a 3-dimensional space. That's going to be a volume. So you have X, Y, and a Z. And you can see if you only had 2 dimensions, you get an area. If you had 3 dimensions, you get a volume. That's R to the third. Now let's define polynomial space. So we usually represent that as P sub some sort of degree. We'll call it degree 2. Now this just means that it's going to be equal to all the different polynomials in the expression A plus BX plus CX squared. And we have to stop there because that's the second degree. Now, these x's are just going to be the basis vectors. We'll define those a little later. But for now, all we need to do is define these real numbers, which are the coefficients in front of those basis vectors. So we'll call that A, B, and C. And we said that we pulled those real numbers from all the real numbers over here, R. And then we'll close it off right there. Let's say that we wanted to find the degree of P of X over here. We would see very easily that the degree is equal to 2. But it could be infinite dimensions if we had x to the infinity. Again, it looks pretty crazy on paper, but all we've really done here is just define a whole bunch of different parabolas that kind of look like this. All right, and of course they could be any plus or minus parabola. In fact, there's an infinite number of parabolas because there's an infinite number of ways to combine A, B, and C. These coefficients, there's an infinite number of those. So there's an infinite number of parabolas in this parabola space, even though we've only got a degree of 2 here. Another familiar space will be continuous function space. We'll represent that as C, and we'll say that it's going from A to B, and this is going to be continuous from A to B. We'll have to define the function by saying we took an f of x, and we need to say that f of x is continuous, and we need to mention that it's continuous along A to B that we chose here, and we're going to map the A to B to this R over here, so the real number line. And there we go. Just like the polynomials, these could have x to some infinite degree power, so these could also be infinite dimensions. The types of functions that could work with this are going to be things like polynomials, which we have here, the exponential, or log functions, or even trig functions. All sorts of normal functions that you could put in here. Let's now define matrix space. So we could say that we have a whole bunch of matrices, M, and they're only going to be 2 by 2s in this example, but we're going to go ahead and say that all the entries come from the real number line R. And so we're going to just basically claim that that's the same thing as saying A, B, C, D, and these are the 2 by 2 matrices, and then we also had to say that A, B, C, and D are elements of the real number line. And so these two things are the same things. Clearly here we have an infinite number of matrices because there's an infinite number of combinations of A, B, C's, and D's which come from R. Another important space is going to be complex space, which has a lot to do with quantum mechanics. So let's try to define that. I'm going to call it a fancy C here. And then for this example, we're going to call it C squared. So we have 2 vectors. So we could say that that's going to be equal to 2 vectors, A1 plus B1, and there's an I there, A2 plus B2, and an I there. So we could see that all the vectors in complex space are all going to have a real component plus an imaginary component. And of course we had to pull A and B from all the reals. And we also have to define that I squared is equal to -1. And there we go, that's complex space. At this point, let's remember that these are all vector spaces, so they all follow the same rules. Well, we can usually refer to the elements in real space as being a V with a little arrow on top of it. We can refer to the elements in polynomial space as being sort of this P with X in the parentheses there, so P of X. We could refer to all the functions here as being F of X, right? And then we can also refer to like all the matrices that we have, we could refer to them as, say, A. So these are just different ways that we can refer to elements in these different spaces. Let's now discuss the laws of vector spaces. We'll start by defining a vector space V as being equal to R to the third, which is going to be equal to all the vectors from negative infinity in 3D space all the way to positive infinity in this 3D space. So we have an infinite number of vectors here. Now, in order to prove that this collection of 3D vectors from negative infinity to infinity can actually be classified as a vector space, we need to follow the laws of vector space. So let's begin. The 10 crack commandments. Numero uno. This one's really important, so I'm going to make it in purple. We're basically going to say that U plus V is going to be an element of the vector space V. And that is true if we have U and V both being elements of vector space V. So we could take any 2 of the vectors inside of here and you have to add them together, and that result is also going to be in that same space. So we could take 1, 1, 1 plus 1, 1, 1, and we're going to get 2, 2, 2, right? Well, it turns out that all of those vectors are inside of that space, and so the first law has been met. Moving on to rule number 2, using the same 2 vectors, we should be able to add U plus V and find that you're going to get the same result if you go V plus U. So those 2 things can be switched around. Rule number 3 is taking those same vectors, we can say that U plus V, and then we can put a parentheses around these and do that addition first, and then add some other vector later, W. And we're going to find that U plus, if we did this addition first, V plus W, then we would actually get the same result. So we can sort of move the parentheses around if we're doing addition. Rule number 4 is also really important. So we're going to say that the 0 vector is inside of vector space V. That means that you could take any vector U and then add the 0 vector and just get back the same vector U. Rule number 5 is that in order to get the 0 vector inside of V, is we had to take some U and then add its negative version, and then that just simply gives us the 0 vector. Rule number 6, another important rule, we're going to say that we can multiply any constant times one of those vectors in vector space V, and of course that multiplication is also in vector space V, as long as we found the constants from the real numbers, and we also found that vector U was in V. Rule number 7, we can take a constant and multiply it by u plus v. And we're going to find that you can distribute that c across. So you can do cu plus cv. And as long as those two things are equal to the same, then that law is met. Rule number 8. We could say that you can take c plus d, these are two constants, and then multiply it by the vector u. And that's going to be the same thing as saying cu plus d times the vector u there. So you can take the u and distribute it across those two constants. Sort of the opposite of that rule. Rule number 9 is that we can move around parentheses when we do multiplication. So we could say that c times d times the vector here, these are the constants, that's the vector, is going to be equal to, well, first you can multiply the c times the d, those are the two constants, and then you can multiply the vector, and that's going to equal the same thing if that law is met. The final law, number 10, is that you could take 1 times the u vector, and that's going to be equal to the u vector. All of these 10 laws must hold if we want to be able to call this group of vectors here a vector space. If we're able to claim that any one of these is broken somehow, then that space is no longer a vector space. What's nice is if we have a subspace, because subspaces automatically inherit 7 out of 10 laws. Let's think of this like trying to make a pizza. Right? Because we know that in order to make pizza, you're going to need to have the dough, which is going to be made from like the flour and the eggs and stuff. And then you know that you're going to have the cheese, which is going to be made from milk. And then you know the pepperoni are going to be made from the pig. So all that stuff has to go into the pizza in order to make a pizza. But let's say we just wanted a slice of pizza. Well, a slice of pizza, it's kind of already implied that you have all those ingredients in there, as long as you have the dough and the cheese and the pepperoni. It's implied that you're also going to have all the other stuff that is required to make those particular ingredients, and so therefore we can claim that this little pizza slice is definitely a subspace of the entire pizza, which is going to be a vector space. It would be nice to have a way to be able to check all 3 of these laws for a subspace W without having to do too much crazy stuff. So let's say we took vector u and added it to vector v and multiplied it by some coefficients a and b, alpha, beta. And then we found that that result was part of the subspace W. In order for this to work, we have to say that we took u and v, these both vectors, are elements of W. So now we know that u and v are both in W. And then we could take our alpha and our beta and we could set that equal to any real number. And so that way we can go alpha and beta are both equal to 1. And if we do that, then we're going to prove this first one, so that u plus v is in the subspace. And then we could set that alpha or beta are equal to 0. And if we do that, then we get this idea that the 0 is in the subspace. Or we could set alpha and beta equal to any other coefficient, any other real number, and we're essentially going to prove this one right here. So we could check all 3 of these laws with just one go right here. That's pretty cool. There's a little problem with scalars. We just defined all the laws for vectors, but scalars are not vectors, so they don't necessarily have to follow those laws. So we could take a look at rational numbers, which is going to be p over q, for example. And we know that p equals 0 is okay, but we know that q cannot equal to 0. But here's the problem. If we take 1/2 and we add 1/2, then we get 1. And 1 is not a rational number. So therefore, we have broken the law of this addition right here. And we can also say that 2 times 1/2 is going to be equal to 1. And so we've broken the law of this one right here. Let's also remember what an irrational number is. It means that there is no possible fraction that can represent this number. It means that there is no possible repeating decimals that can represent it. There is no zeros involved here. And it's going to be all the numbers p plus the square root of q, where q must be greater than 0. And here's the problem. If I take 2 plus the square root of 2, which is an irrational number, and then I subtract just the square root of 2, which is also an irrational number, then that just leaves me with 2. And 2 is not an irrational number. Also, we could take the square root of 2, which is irrational, times the square root of 2, which is also irrational, and that'll leave us with just 2 again, and that is not irrational. So we're breaking these laws here. In fact, these numbers here, these 1s and these 2s, are just integers, and the integers are going to be plus or minus all the whole numbers, and that even includes 0. So the integers actually follow all these laws here, which is cool. The integers follow the laws. The irrational numbers don't follow the laws, and the rational numbers don't follow the laws either. So we can conclude that scalars, you just have to be careful. Some of them will follow the laws like the integers, and some of them will not, like the rational and the irrational numbers.